Hey everyone, welcome back. It's MC again, and let's continue on working through our play of TIS-100. So we finished the first program and talked a little bit about what this game's about in the first episode, and this episode let's move on to some more programs. Alright, so we are doing signal amplifier. Let's check it out. Okay, so our instructions are telling us read a value from in A, double the value, write the value to out A. Seems simple enough. Oh, and a little debug. Let's read it. Computer node diagnostic, microcode dump. July 18th, 1979. Continues to baffle. Chatted with Bernie at IBM, and he says it sounds like something they'd 0n.A come up with in the USSR. But then why is the manual in English? Interesting. So I guess we're figuring out a little bit more about this computer system. It's perplexed our uncle, and now the task is on to us to figure out what it's about. Or maybe he found out. Who knows? All right, so we've got a little bit harder task this time. We're not just moving around numbers. Now we're actually doing some math. So in order to do that math, we've got a couple of tools on our hands. And if I press F2, F1? F1, there we go. Our instruction set quick reference pops up. And so this is a list of all the instructions that we have to work with. Now, if you're familiar with assembly instruction sets, and they're similar between machines, though they're not all the same, you can notice that this one is very reduced from what a typical one might have. So we've got our no-op, we've got move, swap, save, add, subtract, negate, jump, jump if equal to 0, jump if not equal to 0, jump if greater than 0, jump if less than 0, and jump to relative offset. So a very simple instruction list. You'll notice there's no bitwise operators in this instruction set. But that's because the values we are holding aren't bits or bytes. It's integers from negative 999 to positive 999. So that's a little bit different for those of you who are used to computer science stuff and powers of 2. That's a bit of a change. So those of you who are in the know about numbers would say, in the know about assembly programming would say, well, if we want to double a number, why don't we just shift it left or something like that? But there is no shift left operation in this code. And so to explain what a shift left is, I need to explain a little bit about binary. Take the number 5. The double of 5 is 10. But that's not so obvious in decimal. It's not too easy to see how you got there. But if we write 5 in binary, we can actually really easily see what the double is. And the double just happens to be that, followed by a 0. Now, how did I get there? How did I do that so quickly? If we break down any number system, this is true of any base system. So for instance, we use base 10, which has 10 digits, 0 through 9. Binary uses base 2, so it only has two digits, 0 to 1. So base 10, let's take a simple number like 586. What is that number actually telling us? Well, if we break it down, we see that's 1 times 6, 10 times 8, and 5 times, 100 times 5. So we've got 6 ones, 8 tens, 5 hundreds. Add those all up, and that gives you 586. So you can notice that the 1, 10, 100, that's all increasing by a factor of 10. Those are powers of tens. 1 is really just 10 to the 0. 10 is 10 to the 1, and 100 is 10 to the 2. The same is true in binary. So if we take that number 5, what is 5? In powers of 2. Powers of 2 go 1, 2, 4. Oh, 4. Now, 5, to figure out what it is in binary, you take the largest power of 2 that fits into it, and you subtract it. So we get 1 times 4, because remember, it can only be 1 or 0. So we couldn't have 2 times 2, for instance, because binary only has 2 digits. So we have 1 times 4. We have, and we subtract the 4 from the 5. So 5 minus 4 gives us 1. So since 2 is larger than that 1, we have a 0 times 2, since we can't fit a 2 in what's left over. And then finally, that 1 takes care of what's left over. And then if we arrange those in a nice, neat order, we get 1, 0, 1. Okay, let's do that again, but for 10. So let's do our powers again, but instead let's write them the opposite way, descending. So we'll start with 16, 8, 4, 2, 1. Now, 16 is larger than what we want. 16 doesn't fit into 10, so there's a 0 up front. 8 does fit into 10. We put it in, we subtract 8 from 10, and we're left with 2. So we've got a 1 out front of the 8. 4 does not fit into 2, so we put a 0 next to the 4. We've got a 2. 2, of course, evenly goes into 2, so we put a 1 next to the 2, and then with nothing as our remainder, we put a 0 next to the 1. And look at that. We've got 1, 0, 1, 0, which is just our earlier number, 1, 0, 1, with a 0 after it. So whenever you want to multiply or divide by 2 in binary, you just shift your number 1 bit. A bit is a binary digit, 1 or a 0. You just shift it 1 bit to the left. You tack a 0 onto the end. Or if you want to divide by 2, you just remove the last 0. And so if you want, you can go through and you can try this on your own and figure it out. It's really neat how binary can in some ways make math easy. It can be difficult in some ways too, but we don't have that ability in this game, so instead we're going to have to make do with what else we have. And if you'll take a look, one thing that we have is ACC. ACC is short for accumulator. So when we use the add function, it's going to take whatever our add is and put it in the accumulator. Add it onto the accumulator. So if we do add up, we're taking whatever we receive from up and putting it in the accumulator. And then, watch this, if we do, oh, excuse me, we can't do add up. Or maybe we can. Can we do add up? Let's test that. Yeah, okay, yeah, that works. Beautiful. Did you see, by the way, how that climbed to 999? That's because that is the maximum value you can have in this register, or any register, for instance. Okay, so add up will work for our purposes. Additionally, we could do move up, comma, accumulator, and that would work as well. It just happens to take, I believe, more instructions. If we did, so yeah, if we just keep it at add up, I think, no, I guess it's probably the same number of cycles. Okay. Well, regardless, let's keep it at add up because it looks a little cleaner. So we're going to add up to the accumulator, and then we're going to add the accumulator to itself. And what that effectively does when you add a number to itself, that is just an easy way of multiplying it by 2. So there we go. We've got our number multiplied by 2 in the accumulator. And now we just need to get it to out A. So we're going to move accumulator down. And then if we just press Control down, we can move to the next block down. We can type move up, down, Control down, move up, right, control right, move left, down. And that should be a program that executes pretty well for us. Now, you'll notice up here, I've got 3 instructions up here, one here, one here, one here. So is this going to get out of sync with this one? Or what's going to happen? How is it going to behave? Well, the interesting thing about the TIS-100 computer system is that instructions in these blocks loop. So, as soon as it completes this last instruction, it goes back up to the first instruction. So, it's not going to pull another value in and add it to the accumulator before it has moved the accumulator down. And I believe, if we step through this, we'll see for sure. I believe it should clear the accumulator, but I don't know that for sure. So let's just step through it. So it's 22. That's exactly the value we wanted because in was 11. And we're going to move it down. And we've already run into an error. Okay, so we need to clear the accumulator of a value, of the value that it holds after we move accumulator down. So how can we do that? Well, if we bring up our instruction set quick reference, what can we use? Let's see here. Move source destination, swap, count and back. Okay, so how about this one? After we move accumulator down, what if we move, and this is an interesting one, nil accumulator. So we're moving the value nil to the accumulator. Nil is just a special code word in the TIS-100 system that means 0. So if we step through this, is that going to... Yeah, look at that. And that put a 0 in the accumulator, and now it's ready to go for the next run. If we pause it right before it finishes executing, we can see that it is not, in fact... Oh, no, it is. It is doing it exactly right. Our output is matching. The right column is matching the left column. Beautiful. That's exactly what we wanted. And it goes all the way through. Wonderful. Okay. So, here you can see that I got 198 cycles, which is a little bit more, 4 nodes, which is just on, and 7 instructions, which is 1 more than the minimum. So if we move back, we can see why that is. Okay, so we have 1, 2, 3, 4 blocks to get from in A to out A. So obviously 4 is the minimum number of blocks we could have. And we're going to look at that in a second for making this bigger. But let's see if we can't figure out how to get rid of 1 more instruction and possibly shorten this up. Okay, so after some thinking about my code, I realized what I did, and it's kind of silly of me. When you use the add command, it takes the value that you have and it adds it to the accumulator, like we had discussed before. But when you use the move command, it takes whatever value you have at the source and moves it to the destination. So our source is nil, our destination is accumulator. So it'll overwrite whatever is in the accumulator and force the accumulator to take on that value. So if our first instruction is a move, and you'll notice that that was what I put the second time and decided I liked add better because, you know, I don't know, sometimes I just do silly things. But if we do move up accumulator, then you can see that it's going to take whatever's in the up, move to the accumulator, overwrite what's in the accumulator. So let's step through this a couple times. And 22 is in there. We put 24 in there, and 24 got Uh, through it just fine. 32 is working beautifully. 128 is coming out. Okay, wonderful, wonderful. So our output is now matching the output that we can see right here, the predetermined output. And beautiful, look at that. Our cycle count is where most people's were. Our node count is right there at 4. And our instruction count is right there. Okay, so we got the least number of instruction counts and the least number of nodes, but how are there some people with fewer cycles? What's going on there? Let's just save this really quickly, move to a new blank one, and then I'll explain what's going on. So we'll call this one, since we got the least number of nodes and the least number of instructions, we'll just call it NI. Yeah, we'll just call it NI. Sounds good. Okay, so let's create a new program and let's go for the least number of cycles. So what's going on with those other those other programs that are using the least number of cycles, they are doing something called parallel computing. So if you noticed, our program would get a little hung up on this first square because we're doing so much math right here that it takes a while to run through this, and then it spits it out to these guys, which just passes it to the end. So it takes a while to read in, and we're not reading in as fast as we could be. So instead, what we're going to do is we're going to move this out, and we're going to pass it to the right and pass it down. And then we're going to have the math happen here, pass it to this node right here, and then we're going to put it out. And that should hopefully be the fastest that we can do. I'm not entirely sure, but I don't think it would make it any faster to go to all three of these, because I think that the speed that this can take it in would be the same speed that these two can do the math. So let's get to it. So we're going to move up, and watch this, we're going to do any. Now what the any command does when you put it as a destination register is it will move whatever you're taking from the source to any block that is requesting data. So if we go to this one and we say move up accumulator, this is going to try to pull from here, and this, when it sees the bottom pulling, will try to feed the bottom, and this we're going to do move left accumulator. So that move up any is one command that takes care of both of these guys. We could have done move up right, move up down, and it would have just looped through those two, passing it to both of them as it goes. But it's the any command, and it makes it one line of code, so it's one instruction shorter, which is always good, always something to shoot for. So we're going to move up accumulator, add accumulator, and then move accumulator right. And here we're going to do add accumulator, move accumulator down. Okay, so now we're going to be receiving two inputs to this one, but we don't know where they're coming from. So instead of moving up, down, and moving left, down, we're going to move any down. And just like the any, when in the destination, will feed to any block that is trying to take from it, the any, when in a source position, will try to take from any block that is trying to feed it. So it will move any block that's trying to feed into it. Move any down. And then we will just move up, down. So let's step through this. The 11 gets fed in. It's looking, you can see it's trying to feed out to all of those. And it gets taken up by the right one. It didn't get taken up by the bottom one because it can only be taken up by one at a time. And that's just a way that this works. That's So it doesn't pass the same data to multiple blocks, because that would lead to some errors, and that's not functionality that we want. So it arbitrarily, supposedly, picks a block to feed it to instead of feeding it to both. So now 12 is looking for a place to go. The right block is not looking for one currently, so it's going to be the bottom block that takes it. Boom, moved into the accumulator. This one is trying to move 22 down, so we're going to move it, and 22 got moved down. Wonderful. 16 is looking for a place to go. 24 is about to be moved. There we go, 24 is being moved. 16 found a home right here in this right block, and you can see that, look at that, it's going through really fast, and you can see it's already executing faster than what we did last time. 84 commands, or excuse me, 84 cycles, 5 nodes, so it was one more node than what we did with the previous implementation, and then 9 instructions, so a few more instructions, but it was faster. So this is a real world analog to computers and writing code, because sometimes you write code that is longer or more complicated, but in the end turns out faster, and that's what we did right here. So congratulations, guys. We just finished the second challenge, and we're just going to name this C because it was the cycles implementation. And that will be it for this episode. See you guys later. Thanks. Bye.